Greetings, Physics 100 students and people who were on the last lecture and just were too lazy to click the stop button before we went to the next video. In today's talk, we will talk about angular motions. We'll try to understand angular motions. But it turns out if you understand linear motions, you already understand half of this. Because there's a very close connection between linear motions and angular motions. It's kind of like the difference between French and Italian. If you know one, you know probably about half of the other. So there is a relationship between everything in the linear world and the angular world. In the linear world, we have distance, which is a mark of your change in position. In the angular world, we have angle, which is your change in angle. In the linear world, if you move, you have a velocity. In the angular world, you have an angular velocity. Everything's the same, we just put the word angular in front. So angular distance, angular velocity, and of course, angular acceleration. All the equations work exactly the same, it's just that we use a slightly different vocabulary. So instead of distance equals initial velocity times time plus 1/2 at squared, we have the angular distance equals angular velocity times time plus 1/2 the angular acceleration times time squared. And the change of velocity equals acceleration times time goes to the change in angular velocity equals angular acceleration times time. Now, default, if you're given a velocity, especially 1 meters per second, that is a linear velocity. If you're given an angular velocity, it's usually going to be in a different unit. And if you're asked for velocity, probably looking for linear velocity. If you're asked for angular velocity, they usually will specify angular. Now, the units of angles are a little bit different than linear. So we have meters, meters per second squared. In the angular world, instead of using meters, we use a unit called a radian. What the heck is a radian? Imagine a circle. We all know a circle has 360 degrees. But we don't really use degrees in physics. We use radians. One circle has 2 pi radians. So a radian is about 1/6 of a circle. So if your angle is 1 radian, that means you have rotated about 1/6 of a circle, about 60 degrees. A little less than 60 degrees. This is in radians, or rads. This is radians per second, and radians per second squared. Now, the one advantage that angular motions have to linear motions is, for the most part, linear motions have 3 dimensions, and you really have to watch direction. Angular motions only have 2 possible directions, clockwise and counterclockwise. And the weird thing about it is, if I'm rotating a wheel, from your perspective right now, my wheel is rotating clockwise. From my perspective, it's rotating counterclockwise, so it really depends on which side you're standing on. Usually the default is clockwise, but you just have to watch for things that are going backwards. So you don't have to worry about direction nearly as much. We also have other translations as well. Mass in kilograms becomes inertia. Inertia is the angular version of mass. And this is in kilograms meters squared. The linear version of force becomes the angular torque, which is a Newton meter. Don't turn that into a joule. And then, of course, we have an equation for force. Force equals ma. The equivalent is torque equals inertia times alpha, because inertia is mass, alpha is angular, is the angular version of acceleration. So the angular force, or torque, equals the angular mass, or inertia, times the angular acceleration. And then I haven't covered this one yet, but I'll get to that one. So that is the relationship between the linear and the angular world. There's also a translation between the two. So you can convert one to the other, kind of like converting dollars to euros. So that's the kind of similarity. Torque equals force times distance. We'll cover that again. And angular, any angular value other than torque equals the linear value times r. So angular distance, I have that backwards. Linear equals angular times r. There we go. So the linear distance equals the angular distance times r. Let's prove that. 2 pi radians is one full circle. The linear distance around a circle is called the circumference. The circumference is 2 pi r. So if we take 2 pi times r, we get 2 pi r. The linear velocity equals the angular velocity times r, and the linear acceleration equals the angular acceleration times r. In other words, anything that doesn't involve an inertia, the linear equals the angular times r. And when you have inertia, it influences that. All right, so our objective is to understand angular motions. We're going to learn about circular motions, rotational inertia, torque. We'll examine center of mass and what causes stability. We're going to look at centripetal versus centrifugal force. We're actually going to examine centrifugal force a little bit more. Understand angular momentum in a very basic way, and understand the conservation of angular momentum and how that affects our planet that we live on, as well as what it may or may not affect in other places. All right, so circular motions. Previously we examined linear motions. If we're moving in a straight line, we have distance, velocities, and accelerations in that direction. And even if we have two dimensions, we have directions, velocities, and accelerations in each dimension. But what happens if we're not moving in a straight line? What happens if we're going around in a circle? So we're now race car drivers driving NASCAR. Okay. If we're moving in a circle, we have circular motions. Now, we have two things. Now we have angle and we have radius. And those things will possibly change with time. Usually in this class, the radius won't change, so we'll just do that. So if you rotate in a circle, there's a rate at which you're going to rotate in that circle. In other words, you're going to change your angle at some given rate. That rate is called the angular velocity. The angular velocity is the change in angle divided by time. That's like the linear velocity is the change in position divided by time. The units of angular velocity in radians per second. We don't really use degrees per second in this class, or any other physics class for that matter. If you want a linear speed, the conversion is the linear velocity equals the angular velocity times the radius. Now the radius is the radius of the circle that you're rotating around. So if I'm doing this, my center is about here, my distance to the center is about, say, half a meter, that would be my radius. And it's taking me about, what, 2 seconds to go around, so my angular velocity would be 2 pi radians divided by 2 seconds, so about 3 radians per second. My linear velocity would then be 3 times 0.5, which would be about 1.5 meters per second. Let's do a quick example. So we have your 0.5 meters from the center of the merry-go-round. You're going to run the merry-go-round every 3.6 seconds. We're going to skip the degrees per second, find your angular velocities or radians per second. So we're just going to go straight to here, and then you'll find your linear velocity. All right, hopefully you're finished. So, first thing I need to calculate is my angular distance. I do one full circle in 3.6 seconds, so that is 2 pi radians. That's my theta. My velocity, angular velocity, equals my theta divided by my time, which is 6.3. By the way, don't leave things in terms of pi. Usually multiply it out. Pi is 3.14. Going is 3.14159. Go ahead. That's as far as I'm going. I'm not one of those people that know it out to 100 decimal places. That's my graph. Okay, so 3.3 rads divided by 3.6 seconds. We have 2.7 over 3.6, so we have 1.75 rads per second. All right, so that's my angular velocity. My linear velocity equals the angular times r, which is 1.75 times 0.5. Now, a unit's note. A radian is considered a placeholder unit. It's very cowardly. Anytime a radian gets multiplied by a meter, the radian goes away. Now, if you have a meter divided by meter, the meters go away, you have to be left with the distance, then the radians pop back. So they're kind of like groundhogs or meerkats, if you will. So this would be about 0.87 or 88 meters per second. And direction is not so important here because it depends upon fueling a little bit. All right, so hopefully that's fairly straightforward. These are all level 1 problems. Rotational inertia. If I want to rotate something, much like if I want to push something, there's going to be a resistance to that. Now, in the linear world, when I push something, the resistance is called the mass. How much stuff you have gives you how much resistance. So the more mass you have, the more resistance you are to pushing stuff. We saw this example when I was on the skateboard. I had a lot of mass, it had very little mass, and so I had a lot of resistance to motion, changing my motion, so I didn't go very fast. It had very little resistance, so it went like rocket. In the angular world, we call this rotational inertia, or just inertia for short. Newton's laws apply in the angular world, just like the linear world. So to get something to rotate, I have to apply a rotational force. If something's rotating, it stays rotating unless a rotational force is applied to it. The second law holds, force equals inertia times alpha, and the third law holds, well, okay, I guess the third law, not so much. So if I rotate, it continues rotating in the air until something stops it at the same rate. And inertia is calculated. The maximum inertia an object can have is its mass times its radius times its radius. That's the maximum. The minimum is 0. For each piece of mass, the inertia for that piece of mass is mass times radius times radius, where the radius is the distance between that piece of mass and the rotation of the center of rotation of the object. Now, for it to be equal to mass radius squared, all the mass has to be at the same distance. So, for example, if I'm an astronaut orbiting the Earth, all my mass is at the same distance. So my inertia is mass times radius times radius. If I'm a hula hoop going around this way, all my mass is at the same distance. And so again, my inertia is mass times radius times radius. Now for this pen, some of the mass is in the center, and that mass has 0 inertia. The mass on the outside of the pen has much more inertia than the mass on the inside of the pen. And so it is more complicated. So what we do is we usually use what's called a constant times mass times radius, where the constant depends upon the shape of the object and how it's rotating. Unless you're in a calc-based class, then you just have to straight calculate it. Involving fancy math that we don't do in this class. So, the further the mass is from the center, the higher the inertia will be. And of course, the higher the mass is, the higher the inertia will be. And if the inertia is higher, it's harder to make it spin. And if the inertia is small, it's very easy to make it spin. So it's much easier to make this pen spin like this, where all the mass is near the center, than it is to spin like that. So it spins much faster like this than it does like that. Although that's kind of hard to see on the camera, probably. So here are some examples. These are just examples. Usually you'll be given these on tests. You won't be expected to memorize these particular ones. Please note for meter sticks, instead of by radius, it's usually times the length of the stick. That's the one deviation from the mr squared. All right, so I'm going to skip over this because I'll be honest, inertia is a almost always level 1 problems unless you're in a calculus class. A lot of times you're being just given inertia. Really we want to focus on the more important concepts such as torque. So torque is kind of important. So torque is the angular version of force. If I want to get this to rotate, I have to provide torque. Now, if I provide a force in the linear distance, in the linear direction, it provides a linear acceleration. My 4 pins. Okay. Only 1 pin is harmed in the making of this film. But if I hit it perpendicularly, like this, you can see it rotates. And that is what's called torque. So torque is the force, it is either force times distance from rotation point or inertia times rotational acceleration. So what that means is the torque, if I provide a linear force that is perpendicular to the surface, it's going to create torque that's equal to the distance between the rotation point times the force. Now the rotation point is going to depend upon whether the object is free or if it's bolted down. If you have an object that's not held down, the rotation point is going to be what's called the center of mass. In this case, the center of the object. So the center. If it's held down, wherever it's gripped at, let's say I grip it here, that's going to be my rotation point. So it's going to rotate at this point here. And so my torque is going to be this distance times my force now. Now this is very important because in the real world, we sometimes need to unscrew things. And sometimes that can be very difficult. I'm looking at you, pickle jar. I think you can hide from me on the other side of the person's computer. I know where you're at. Always difficult to unscrew those. Sometimes you have little screws that are tough to get off, like lug nuts on a car. So what do? Well, we have put in this big device like a wrench that has a very long distance, and we can hit it from a very long distance. And that distance allows us to create a very large torque for some given force. Okay, it doesn't quite apply to the pickle jars, because usually we don't have wrenches for pickle jars, but for the lug nuts we do. And then once we have that torque, we can actually set force times distance equal to inertia times rotational acceleration. And that'll allow us how much we're accelerating. So if I have a wheel and I hit it on the end, I can do that force times distance and set it equal to inertia times rotational acceleration. Calculate the inertia for a bicycle wheel will be mr squared because it's all the same radius. And that can give you the angular acceleration of the wheel. You may want to wait to the end of the video to try that. Okay, you're back. You went and tried it. So those are the two equations. So let's do a torque challenge. A playground challenge, if you will, which you may or may not have done as a kid, and I don't know inside of the challenge you were on. So we have two kids. Smaller one and a bigger one. The bigger one, for some reason, is convinced that if he or she sits close to the center of the seesaw, that they'll get more bang for their buck. So they sit 0.7 meters from the center. The other kid, smaller, sits at the end of the seesaw. So we have the seesaw like this, we have the smaller kid here, and we have the big kid here. Now the question is, which kid is going to end up in the air? Go ahead and calculate this. Go. Now if you wonder where the force is going to come from, what force is coming this way because of each of these people? Think about that. All right, let's solve it. Torque of the big kid equals force times radius. Now the force is going to be mg, in this case, his mass, times the radius. So that is 60. And if this is the first one of these videos of mine you've been watching, I, in this class, for my Physics 100 class, use 10 for G, just to make the math more straightforward, instead of the actual 9.8. So I guess my class exists on a slightly more massive planet. Okay. And it's down times 0.7 meters. Now, the way I've drawn this, down is going to give me a counterclockwise torque. So that my answer is going to be counterclockwise. So I have 600 times 0.7, that's 420 Newton meters counterclockwise. CCW is counterclockwise, CW is clockwise. So 420 counterclockwise. Now what about the smaller child? Again, we have mgr, but this time the mass is only 30 times 10. But the radius is 2.4 meters. So big radius, small mass. Now we do the math. 300 times 2.4 is 720 Newton meters. If we read it off the chart the way we've drawn it, always helpful to draw. Always helpful to draw because I can draw it the other way, in which case this will be clockwise and this will be counterclockwise. He's going to go this way, which is clockwise. The only reason that these directions will be important is if I add the two together, because they're opposite directions. Now notice the smaller kid wins. He has a bigger torque. Now I can go one step further and calculate the net torque. Much like we have a net force, if we have if we have multiple forces on an object, we can calculate the net force. We can also calculate the net torque. So I would take 720 counterclockwise minus 420 because it's the other way, and I would get that the net torque is 300 Newton meters clockwise. I could then set that equal to I alpha and solve for alpha. I would have to calculate I, and in order to do this, I would just have to calculate the inertia of the beam plus the inertia of him plus the inertia of him. And then I would get the total inertia, and that would then allow me to calculate for alpha. But that's more geared for the trig-based class than for this class. So that's all we have for that. Which is why I don't write it anymore. Center of mass. The average position of mass in each dimension gives you the location of the center of mass. The center of mass for an object does not have to be in a place of the object that actually has mass. So let's think about that. We have a soccer ball or basketball. Where's the center of mass of the ball? In the center, right? Is there mass? Ignoring the air? There's not. And so the center of mass is in a place where there is nothing. So why is center of mass important? Well, it's important because in rotations, things will rotate around the center of mass. So a soccer ball will rotate around its center. A hammer, if you rotate the hammer, will rotate around the center of mass of the hammer. So if I have a hammer, its center of mass is going to be about maybe here, and so it'll rotate around that point if you spin it. And then maybe a little bit further down. Don't get the hammer, you got the hammer. Don't break, you broke the lamp. I'm not responsible for broken lamps because of rotated hammers. That disclaimer. Okay. And do not bring the broken lamp to class. And go, see what I did? I don't want to know. Okay. So, what other things are center mass important for? Well, it turns out it's important for stability. This is more engineering than physics, but it's important as well. So imagine if I do this. What happens to my center of mass? Now right now my center of mass is about the radical center of mass. As I crouch down, what happens to my center of mass? Well, my average mass now goes down because I have more mass closer to the ground and less mass above the ground, and so my center of mass will lower. If I lean forward, my center of mass will now move in the horizontal direction because I now have mass this way, and it'll move that way. Now the question is, how far can I lean forward before I fall over? Well, let's test it. Now I'm going to do this over this. When I fall, I'll fall on the table. Right about there. Okay, so what was special about that? Well, if you look at where my center of mass is, as I lean over, my center of mass moves. Here's my feet, here's me. My center of mass moves over and over and over and over and over. When my center of mass hits the end of my toe, I fall over. For something to be stable, the center of mass has to be supported by your base. If it is not supported by the base, it falls over. So if I have 2 feet like this, imagine I'm standing on the wall. This is my base, even though I don't have feet here. But my feet provide the base. As long as my center of mass is anywhere in this box here, I'm okay. If my center of mass comes over here, I fall this way. Unless my foot goes out, now I have a bigger base. If my center of mass goes out here, like I'm leaning, either I have to put my foot forward, now I have a bigger base, or I just plain fall on my face. All right. And the reason being is that now gravity is going to pull, and gravity is going to create a torque now. So I'm leaning over like this. My base is over here, and my center of mass is now here. Gravity is going to pull down, but now it's going to rotate me, and I can no longer stop that rotation. And so I'm going to be torqued, and you fall in over. All right. And so you got to make sure your center of mass is always supported. That's why wheels and cars tend to be on the outsides, so you have a really big base. All right, moving on to the next topic. Actually, let's take a pause here and go to the next 30-minute YouTube video, because I'm betting in this point it'll do it automatically anyways. And this is usually my day 2 stuff, or my second hour stuff, so we'll pause it.